We're tackling a problem where a support vector machine, SVM, which should produce a straight decision boundary because it uses a linear kernel, is unexpectedly creating a curved one. I'll guide you through figuring out why. This is a multiple-choice question to test your understanding of SVMs and how their decision boundaries are visualized. This sets the stage. We're using a tool called DecisionBoundaryDisplay from a Python library named Sklearn to show the boundary of our trained SVM. The SVM uses a linear kernel, implying it should produce a straight line. But it doesn't. Let's find out why. This is a key concept. If the data points can't be separated by a straight line, even with a linear kernel, the boundary won't be straight. A soft margin will be used. Plot underscore method setting in our visualization tool influences how the boundary is shown. ISO creates contour lines, and these can appear curved even if the underlying boundary is straight. The C parameter controls the margin softness in the SVM. A small C allows for a wider margin, possibly leading to a curved decision boundary even though a linear kernel is used. It's like the SVM is compromising to include more data points. If the features, variables, in your data have different scales, it can distort the apparent relationship, making data that's actually linearly separable look nonlinear. Think of it like stretching one axis of a graph. A straight line might become curved. These are the possible reasons for the unexpected curve. The data itself might not be suitable for a simple straight line separation. I'm investigating why a linear support vector machine, SVM, produces a curvy decision boundary when it should be a straight line on a 2D dataset. It's a bit of a puzzle. This is the core question of the problem. I'm trying to figure out what could cause the unexpected curve in the decision boundary of my linear SVM. The plot underscore method parameter in the DecisionBoundaryDisplay function determines how the decision boundary is displayed. If it's set to ISO, it creates contour lines, which can make a straight line appear curved, depending on the contour lines. It's like looking at a straight road from an airplane. The road might seem to curve because of perspective. The C parameter in an SVM controls the trade-off between maximizing the margin and minimizing classification errors. A small c creates a soft margin, allowing some points to be misclassified. This can lead to a less distinct, potentially curved, boundary. If features aren't scaled appropriately, for instance, one feature has values ranging from 0 to 1, and another from 0 to 1000, it can distort the data, and what looks linear in one scale may look nonlinear in another. It's like trying to draw a straight line on a stretched rubber sheet. The line will appear distorted. Even with a linear kernel, if the data points themselves cannot be cleanly separated by a single straight line, the resulting decision boundary will not be perfectly linear. The algorithm will try its best but will need to compromise, resulting in a seemingly nonlinear boundary. I think all the options above are possible reasons. That's why I'm breaking down each one to understand what might be happening. It's like detective work. Hey Vamsi, let's crack this mystery. We're looking at why a linear support vector machine, SVM, which should produce a straight line, is giving us a curvy decision boundary. It's like trying to draw a straight line on a crumpled piece of paper. The paper's wrinkles, our problems, make it look bent. Imagine you're measuring distances, but one ruler is in centimeters and the other in miles. Your measurements will be all over the place. Similarly, if your data features have wildly different scales, it can mess up the SVM's perception of linearity. It might think it's seeing a curve, when in reality, it's just a scaled-up straight line. The fix? Feature scaling. Make sure all your features are on a similar scale, like standardizing to a mean of 0 and a standard deviation of 1. The C parameter in an SVM controls the trade-off between maximizing the margin, the gap between classes, and minimizing classification errors. A small C means you're prioritizing fewer errors, even if it means a smaller margin. This can lead to a decision boundary that bends to accommodate outliers or misclassified points, making it seem nonlinear. Think of it like this: you're willing to bend the rules a little to get the best fit possible, even if it means the straight line isn't the perfect separator anymore. Sometimes, no matter how hard you try, you can't perfectly separate data points with a straight line. This is data that is non-linearly separable. Even a linear SVM will struggle to create a perfectly straight boundary in this case. Instead of a perfectly straight line, it will attempt to find the best possible straight line, which can look curved due to constraints, particularly if using a soft margin. The _plot_ method in the DecisionBoundaryDisplay function affects how the boundary is visualized. ISO creates contour lines, which might make a linear boundary seem curved, similar to the way contour lines on a map represent elevation changes, even if the underlying terrain might just have a simple slope. Let's explore why a linear SVM might show a curvy decision boundary, even though it should be a straight line. I'll break down each potential cause. Imagine trying to separate two groups of dots on a piece of paper with a single straight line. If you can't do it, the data is not linearly separable. A linear SVM will try its best, but the resulting boundary might bend to accommodate the messy data. That's why you might see a curve. The C parameter controls how strict the SVM is. A small c means the SVM is more tolerant of misclassifications, points on the wrong side of the line. To minimize errors, it might create a curvy boundary even if the data is mostly linear. Think of it as bending the rules a bit to fit the data better. The _plot_ method setting in DecisionBoundaryDisplay affects how the boundary is shown. ISO uses contour lines, which are like elevation lines on a map. Even a perfectly straight boundary can appear curved if the contour lines aren't perfectly aligned. Imagine one feature is measured in centimeters and another in kilometers. The SVM will be more sensitive to changes in the kilometer scale. This can distort the relationship between features, making data that is actually linearly separable appear nonlinear. Applying feature scaling, like standardization or normalization, levels the playing field, giving all features equal weight. I see a problem. You've trained a support vector machine, SVM, using a linear kernel, meaning it should create a straight line to separate data points. But the decision boundary is curved. This is unexpected and needs explaining. This means the data points are all mixed up and cannot be separated by a single straight line. Even with a linear kernel, your SVM will try its best, but the boundary might look curvy because it's compromising. DecisionBoundaryDisplay tool plots the boundary using contour lines. If you use the ISO method, the contour lines, even with a perfect straight line boundary, could look curved in a 2D plot. It's a visualization trick. The method controls how the boundary is shown, not necessarily the shape of the boundary itself. The C parameter in an SVM controls the margin softness. A small c means you're okay with a few misclassifications and a wider margin. The boundary tries to include these outliers and can, therefore, appear less straight or even bendy. Features, data columns, might have very different scales, like one being in centimeters and another in kilometers. This imbalance can skew the linear relationship and lead to a nonlinear looking boundary. Even if your data is linearly separable, the different scales hide that relationship. Imagine you're trying to draw a straight line to separate two groups of points. If the points are all jumbled up and can't be separated cleanly by a single straight line, a linear SVM, even with a linear kernel, might still try its best, resulting in a slightly curved, not perfectly straight decision boundary. That's because the algorithm might make some compromises to accommodate the messy data points. This is just an approximation of a true linear separation, the best it can do given the situation. It's like trying to fit a straight line to a squiggly curve. You'll never get a perfect match. Let's say your data points are scattered all over the place and cannot be separated by drawing a single straight line. Even if you use a linear kernel SVM, which should ideally create a straight decision boundary, you will get a curved decision boundary because a linear kernel simply cannot find a perfect separation. The SVM will still try to find the best fit, creating a decision boundary that attempts to minimize errors but isn't perfectly straight. The _plot_ method parameter in the DecisionBoundaryDisplay function determines how the decision boundary is visualized. Setting it to ISO means you're creating contour lines showing equal probability. Even if your actual decision boundary is a straight line, the contour lines plotted might appear curved, giving the wrong impression that the underlying decision boundary is curved. It's like drawing contour lines on a hilly landscape. Even if the hill itself is a simple cone, the contour lines will show curves. The "C" parameter in SVM controls the penalty for misclassifications. A small "C" value indicates that we accept some degree of misclassification, creating a soft margin. This means the SVM will create a decision boundary that might not be completely straight, allowing for some data points to be on the wrong side of the boundary. Think of it like this: you're trying to draw a line to separate red and blue dots, but a small "C" allows some red dots to be on the blue side, and vice versa, resulting in a boundary line that is not exactly straight. Feature scaling is about making sure all your features have a similar range of values. If one feature has much larger values than others, it can disproportionately influence the SVM, potentially making a linearly separable dataset look nonlinear. It's like trying to draw a line on a map where one axis is in kilometers and the other in millimeters. The line will appear very skewed, even if the underlying relationship is linear. We're investigating why a linear support vector machine, SVM, which should produce a straight decision boundary, is showing a curvy one when visualized using Sklearn's DecisionBoundaryDisplay. It's like expecting a perfectly straight line but getting a squiggly one instead. We need to figure out why this is happening. Why isn't my linear SVM's decision boundary a straight line? That's the puzzle we need to solve. We are using a linear kernel, which means the model learns a straight line to separate data points. I suspect the way we're visualizing the boundary, using the ISO setting in DecisionBoundaryDisplay from _estimator might be creating the illusion of a curve. Imagine plotting contour lines on a map. Even if the underlying terrain is flat, the contour lines can appear curved depending on how they're drawn. The ISO parameter draws contour lines. It could be giving us a misleading image. A small c value allows for a soft margin, SVM. This means the SVM allows for some points to be misclassified in order to find a better decision boundary overall. This can lead to a curvy boundary even if the model uses a linear kernel. It's like giving the SVM a little flexibility to wiggle the line to minimize errors, even if it means it's no longer perfectly straight. Let's say you have features measured in different units, like height in meters and weight in kilograms. If you don't scale them, the SVM might emphasize one feature over the other, distorting the perceived linearity of your data. It's like trying to draw a straight line on a grid with uneven spacing. The line might look bent. Applying feature scaling before training the SVM ensures that each feature contributes equally to the decision boundary. Even with a linear kernel, if your data points can't be completely separated by a single straight line, the SVM will attempt to find the best approximation, possibly resulting in a somewhat nonlinear-looking decision boundary. It's like trying to draw a straight line through a bunch of points scattered all over the place. You'll never get a perfectly straight line that separates everything.